Okay, g'day all, welcome to another tute. Today I want to talk about Boolean instructions in assembly with Linux. We're going to be looking at the Boolean instructions, or Bitwise instructions they're sometimes called, and anybody that's coded in C++ is probably familiar with these already. They're used to make if statements. More often than not they're sort of used with these operators here, this ampersand, the pipe, and this weird little caret thing. Anyway, 0 is generally considered to mean false in computing, and 1, or often any non-zero value, means true. And these instructions let us build complex logical conditions. They allow us to mask out and manipulate single bits. They allow us to encrypt data. Further than that, though, they're pretty much the most fundamental level of what the CPU's actually doing. Yeah, the way that it performs arithmetic. Anyway, before we go on to the instructions themselves, I want to explain truth tables. So, when we write out a Boolean instruction, you'll often see it written out with a truth table. The instructions take two inputs each, except for one of them. And what you do is you write out every possible combination that those two inputs could have. So, if those two inputs are either 1 or 0, then we've got 4 combinations. 0, 0, 0, 1, 1, 0, and 1, 1. And then in the output column for a truth table, you write out what the output from the instruction would be. So this happens to be the truth table for Boolean AND, as we'll see in just a minute. But to read the truth table, what you would do is you would say, well, if A is 0 and B is 1, the output is going to be 0. So you just read across from left to right. So for Boolean AND, as we'll see in a minute, the only time it returns a 1 is actually if both of the inputs are 1. Anyway, that's a truth table. You'll often see them written a bit backwards as well. A lot of people prefer to write 0, 0, then 1, 0, 0, 1, and 1, 1. I don't know. I like this way because it's it's the same as binary. 00, 01, 10, 11. Anyway, it's up to you. Okay, so moving on to one of the Boolean operations. So we'll look at just the Boolean operations in general first, and then we'll look about how they're implemented in assembly. Okay, so the first one is Boolean AND. This returns 0 for all inputs except when both inputs are 1. So it's pretty much the same as asking, are both inputs 1? And it'll give you a 1 if the answer is yes, or a 0 if the answer is no. And it's similar to the meaning of the English word and in the sentence, is it raining and nighttime? So for the answer for that question to be true, or yes, it would have to be raining and it would have to be nighttime. So if 1 or both of those is false, then you would have to answer no, it's not raining and nighttime. And is sometimes called the conjunction. Not by me, I call it and. There's a few symbols for that are used in different Boolean algebras for and. I tend to stick with either the ampersand, that B is meant to be over here, the ampersand symbol, that weird little 8 looking thing, or I just write the word and the assembly instruction is and, A-N-D. And the first operand is your destination in Intel syntax. In AT&T it's actually the swap your operands around, and don't forget your suffix as well. Okay, Boolean OR, the second operation. So Boolean OR returns 1 for all inputs with 1 or more 1s. So what it's kind of asking is either or both inputs 1? And if the answer is yes, then it'll give you a 1. If the answer is no, then it'll give you a 0. It's similar but not quite the same as the English word or. So in the sentence, is it raining or nighttime? The English word or would kind of mean that it can't be both. Do you know what I mean? So if it's raining and nighttime, then in English you would kind of say no to that question. But Boolean OR is different. So if you want something closer to OR, you'd actually use exclusive OR or XOR, which we're about to have a look at. Boolean OR allows for both operands to be 1. So this is the truth table for Boolean OR just here. The output column is 0, 1, 1, 1. It's sometimes called the disjunction. Again, I don't personally call it the disjunction, but you might hear that. And there's a bunch of different operators for OR as well. So the plus symbol, this weird little V looking thing. You got the pipe, which is the one that I usually use because I got that from C-like languages. Or of course you can just type the word OR. And in assembly, the instruction is the word OR. So OR, RAX, RDX is going to OR the bits of RDX and RAX, and it's going to store the result in RAX. Once again, if you're AT&T syntax, you put your suffix there and you swap your operands around. Okay, that's Boolean OR. Okay, moving along. Now we got NOT. Okay, so NOT is the only one of these instructions that takes a single operand instead of two. And it's really, really easy. All that it does is flips the bit. So if the bit is 1, it becomes a 0 in the answer. If the bit is 0, it becomes a 1. It's as simple as that, really. And if you're not the original, if you're not a value twice, you get back the original, which is pretty good. So 0 NOT gives you 1, and then if you NOT that 1 again, you get 0. Good stuff. Okay, so NOT is sometimes called the bitwise complement, the ones complement, or just the complement. And some of the symbols you might see are these ones. Yeah, I tend to use the exclamation mark myself, just from programming C all the time. And in assembly, the instruction is NOT, like this, N-O-T. Good stuff. Okay, and this is the last instruction that we'll look at. This is XOR, or exclusive OR. This wasn't one of the original operations defined by Mr. George Boole back in, I think, like the 1800s or something like that. This logician or mathematician, George Boole, invented Boolean arithmetic, or Boolean algebra, and his original specifications for the algebras was only AND, OR, and NOT. Yeah. But XOR means either A or B, but not both. So XOR is similar to the English word OR. You can have one or the other, but not both. So, if somebody says you can have an apple or an orange, they kind of mean that you can't take both. So that's similar to XOR. This is it down here. So the truth table for it, if you have a bit of a look at this, you might work out that it's actually the same as not equal to. Yeah, so if A and B aren't equal to each other, you get a 1. Otherwise you get a 0. So 0, 1 gives you a 1, 1, 0 gives you a 1. But 0, 0, the A and B inputs are equal, so you get a 0. And same with 1, 1. Okay, so that might be one way to think of it. You can XOR, what's this? You can XOR two parameters and then not the result to see which bits are the same. yeah, you can. It's not really the time or place for that, but yeah, it's an interesting little bit hack. We might have a look at that in the coding if we get time, but you can do lots of weird things with XOR. It's very interesting. Anyway, the syntax for XOR is just XOR and then your two parameters. I'm not sure if I mentioned previously, actually I'm sure that I didn't. But you can use a memory operand for these as well, so you could say XOR memory RDX or XOR RAX and then memory. Yeah, it's up to you. All good, but don't use two memory operands. Yeah, that won't work. Okay, so now we'll start to have a look at exactly how this works in a computer, because it's not quite that simple in a computer. So the CPU doesn't perform operations on single bits. It can't. It never does. It always works with bytes, words, Dwords, or Qwords. So that's 8 bits, 16 bits, 32 bits, or 64 bits at once. And when a Boolean instruction is performed between two operands, what happens is it's performed in parallel between the corresponding bits. So for bytes, and that's what I've illustrated down here, what it means is that 8 copies of the Boolean instruction will be performed at once, which is pretty cool, really. Especially when you move up to 64-bit words. In that instance, you're getting 64 bitwise operations, all in parallel, really, really quickly. These are really fast instructions. These are some of the fastest instructions in the whole CPU. Okay, so here's a bit of an example. I've just got 2 bytes. So if you want to refer to the truth table for Boolean AND a few slides back, this is the A and B columns here. This is the A up the top and B down the bottom. And what we want to know is what is the result of ANDing those two operands together. So this is the output column down the bottom here. Well, there you go. So that would be the result down there. What happens is that each byte is ANDed with its corresponding bit in the other operand. So 1 and 0 gives you a 0. 1 and 0 gives you a 0. 0 and 1 gives you a 0. 1 and 1 gives you a 1. 1 and 0 gives you a 0, then we get another 0, and finally on the end we get another 1. Yeah, so 1 and 1 gives you 1. So this yellow down here would be the final output from ANDing those two bytes together. And if you're in x86 assembly and you've only got 2 operands, it would be this output value that would be saved to that first operand in Intel syntax, or to the second operand in AT&T syntax. Okay, that's good, but who cares? Well, what's surprising about these little operations, these little bitwise operations, is that All finite logical operations and mathematical statements can be modeled using only AND, OR, XOR and NOT. Weird, eh? You actually don't even need that. For instance, when a computer adds two integers together, it doesn't use base 10. You probably know already that the computer uses binary. But I'd probably go a little bit further than that and say that the computer doesn't even know binary. Really, at the heart of the CPU, all it knows is these Boolean operations. When you XOR two bits together, what you get is the result from adding those two bits. And when you AND two bits together, you get yourself a carry in binary. Sweet. So a CPU can add 2 million digit numbers in the blink of an eye. They are so fast. Nowadays, a modern CPU is so fast. But what it's actually doing is just millions and millions, billions of these little Boolean operations with electrical signals coming in and out of its pins. So the CPU is nothing but a gigantic collection of transistors etched into silicon. Yeah, and the transistors make these Boolean operations with logical gates. But it's not really the time for that. If you want to make a few of these logic gates, it's fun to play around with transistors. Go and get yourself some wire and an LED, a couple of transistors. Anyway, what we end up with, if you get enough transistors together, you can multiply, you can take square roots, play an FPS game, a song or a movie, you get a computer pretty much. I shouldn't downplay a CPU, they are more than transistors, but yeah, the logic units are mainly transistors. Okay, so we're going to move on to coding. I'm going to do this, I don't know if you want to have a go at it. I didn't really specify enough information for anybody to have a go at this themselves, but I don't know, you might want to. I'm also in Windows at the moment, so I'll jump over to a virtual machine, and I'll see you there. Okay, g'day, I'm back again. It won't seem like I went anywhere, but I did. It's been hours, actually. Anyway, magic. Okay, so what I want to do is just code up these little examples. This is mostly just to, I suppose, provide a bit of an example of, a visual example of these bitwise operations. So I've got my print bits function just here, which prints out the bits of an integer. It's got the most significant bit over the left-hand side and the least significant bit over the right-hand side. So I'm going to be using that to print out the bits while we go. And in my assembly file, which I'm linking that main file with, it's got nothing at the moment. Yeah. The make file, if you want to see the make file, I think it's exactly the same as the make file for our previous projects. Yeah, it just looks like that. Okay, but on to the first question. So I might just name these question... sorry, I didn't really write out these instructions clear enough for anybody to have a go themselves, but yeah, after I've done this little demo, or even now if you want, you might want to just write out something like this as well and play around a bit more with these bitwise instructions just to get used to what they do if you've not coded in C++ and come across them before. Anyway, do whatever you want, really. Question 1. It's going to ret at some point. Okay, so I might just x times c and int question 1, int a, and int b. Okay, so this is going to return the OR of two parameters. But what I might do first is just print out the bits to my two parameters. So 2783 and 1552. Just so that we get an idea of what the input parameters are like. Okay, I'll give that a save. And here in my assembly, we'll actually do the OR. So those two parameters, those two integers, they're going to be passed in registers EDI and ESI. So I might just mov EDI to, whoops, other way around, EAX, and then perform the OR. So OR, EAX, and ESI. So you've got to move your parameter to EAX because that's what C++ is going to return, read as the return value. Alright, let's have a look. Make and run. Well, I didn't print out the... that was silly. Yeah, sorry, I forgot to print out the actual function call there, so how embarrassing. Okay, we'll try that again. Make and run. Okay, that's better. Alright, so now we see the top line just there is the 32 bits of 2783 in binary. The next line is the 32 bits of 1552 in binary, and the lowest line here is the output from the OR instruction, just here. The OR of those two 32-bit integers. So what you can see is that it's pretty much followed that little truth table that we had for OR earlier in the slides. 1 OR 0 gives you 1, 1 OR 0 gives you 1, blah, 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 blah. 1 OR 1 gives you 1 as well. In fact, the only time that we get 0 in our result is if neither of the two input operands had a 1. So right there, for instance, 0 OR 0 equals 0. Alright, good stuff. So that's OR. That's pretty good. Let's move on to the next question, which is almost the same. Question 2. I might just copy. What the? Where's my cursor gone? Here we go. And run question 2. Question 2 is XOR those two values. So if I just get that back into the focus. So it's the same as question 1, only the instruction is XOR. Let me just copy this and question 2, and I think we're ready to roll. Okay, let's have a look, see if we can make this. I say make this, please. And run me. There we go. Okay, so the results from XOR are almost the same as OR, except whenever there was a 1, 1, you know, both 1s in the input operands, XOR results in a 0, where before, with regular Boolean OR, that was a 1. Okay, so that's a little bit about XOR, but I did want to also explain. Well, we'll go on to the next one, and then I'll show you a trick. It's pretty cool. The next question is, what happens if you XOR the result from the above, that's this original XOR, with 1552 again? Well, I already know the answer, and you might too if you've programmed for a little while. What happens if we XOR EAX with ESI again? So remember that ESI is 1552. Let's have a look. Question number 3. Okay, let's see if that works. Make no. Undefined reference to question 3. What have I forgotten? Here we go. I forgot to mark it as global. Wake up. Okay, make. Okay, there we go. Okay, so the top line, once again, is the bit pattern for 2783. The middle line is the bit pattern for 1552. And the lowest line, if you're observant, you might note, is exactly the same as the top line. So the answer to that question, what happens if you XOR some value with another value twice? You get back your original value. Which is kind of why XOR is really useful in encryption. Yeah, mind you, encryption's obviously a little bit more complicated than that. You know, you've got public keys and all sorts of things, but XOR is definitely in there somewhere. Anyway, moving along. What I wanted to say was, in the slides, I mentioned that you can, well, if you XOR 2783 and 1552, what you end up with is a bit pattern which is 1 for every time the bits in those two operands are different. So what you can do then is a population count, or POP, CNT, population count. That's an instruction that counts the number of 1 bits in the parameter. Yeah. So what this is going to give me now, it's not going to return, you know, the XOR or whatever. What it's going to give me, if I just call it cout, what is it, question 3, and I've forgotten my parameters again. What it's going to give me is what's called the Hamming distance. Yeah, or the number of bits that are different between the two parameters. Let's have a look. And it's really fast too, it's really fast. You never used to be able to do this. The number of bits that are different between the two numbers, 2783 and 1552, is 8. Easy as that. So, what I was saying before, if you not this value, the XOR, if we XOR EAX and ESI, but then we not that value, well, you don't need two parameters. What we'll get there is the opposite of the Hamming distance. We'll get how many bits are the same between the 32-bit integers, 2387 and 1552. So let's have a look. It should be 32 minus 8, if maths is right. And what do you know it is? So 24 is the answer. There are 24 bits that are the same in 2387 and 1552. Yeah, and that's a super fast way to do you know, these Hamming distances and count the number of bits that are the same between integers. Much faster than what you generally get from some C++ algorithm. Anyway, let's just move on to the last question. So this is question number 4. I might just copy question 3, even though it's completely different. I'll just delete all that. So what's the question? Not 129 and increment your result with ink. What do you get? Okay, I don't know how many people know this, but let's do exactly that. So first I'll mob EDI, I'll mob EAX EDI, because EDI will be the 129. That'll be the parameter that I pass. And if we not EAX and then we ink EAX, what are we going to get? Let's have a look. Okay, 129 is the parameter. And it's question number 4. Let's see what we get. Make. I might just, whoops. Give me a clear, mate. What's the problem here? What's the problem? Well, the problem is that you'll give the you've got 2 parameters in the prototype. Nope, that's not the problem. Undefined reference to question 4. Okay, we got question 4 there. Did I? Aha! Forgot to mark it as global. Try again. Ah, there we go. Okay, so what do you get if you not 129 and increment it? Well, you get negative 129. Yeah, so the bitwise not plus 1 of an integer is the 2's complement, or the negative version of the integer. Yeah, so C++ reads that as the 2's complement, or negative version. Likewise, if we had another number, say, or just a random number, but it was negative, if we not that number and increment it, we'll get positive 12399. Yeah, there you go. Anyway, the easier way to do that is just to say neg. Yeah, neg, EAX. That'll do the same thing. 2's complement. Anyway, I hope that was interesting, and thanks for watching all, and have a good one. See ya.